Hello everybody, I'm Anton Tiepner and I would like to present to you some of my current research on nonparametric velocity estimation from local measurements. This work is in cooperation with Markus Reist from Humboldt University of Berlin and Claudia Strauch from Aarhus University, my current PhD supervisor. I will start my talk with a little bit on statistical inference for SPDEs, followed by a detailed explanation of local measurements, which is then be used to construct an estimator for the unknown velocity. The first question that comes to mind is, what exactly are SPDEs? Well, we can interpret them as an infinite-dimensional version of ODEs with some noise in its dynamics. We will focus on the concrete setup of an elliptic SPDE, meaning we have a second-order linear operator A, and the SPDE equation dx of t equals ax of t dt plus dwt. So we will work in the simplified setup where this equation holds on the unit square with initial condition x0 equals 0, and we have typically boundary conditions. We are interested in the unknown velocity theta appearing on the operator A defined by az equals to diffusivity coefficient A times second derivative of z plus divergence of theta times z. So those SPDEs are used to model transfer, dispersion, spread, and so on from of quantities like heat, mass, energy, liquids, etc. But why should we work with SPDEs in the first place? Well, in this figure, you see on the left-hand side an SPDE, a PDE in the center, and a PDE with added noise on the right-hand side. And the dynamics between SPDE and PDE with noise differs significantly. And this can also be observed in real data. So SPDEs are useful to consider. What options do we have to do inference? Well, you will all know the maximum likelihood estimator. And for stochastic processes, they normally can be constructed by some variation of the Sarnoff theorem. And also method of moments estimators can be useful. For our concrete setups, we have three approaches. First of all, the spectral approach, where we observe continuously in time Fourier modes of the solution for an orthonormal eigenbasis EI of the operator A. And this leads to independent Ornstein-Uhlenbeck processes, which dynamics are well understood. And we can use them to construct the MLE directly. And the number of observed modes determines the convergence rate. Then we could also work with discrete observations, meaning that we know the solution on a space-time grid. And the estimation uses a method of moments and increments in space and time to construct an estimator. So basically the frequency of our space-time grid determines the convergence rate in this case. And third, we can work with local measurements, which were recently introduced by Altmaier and Reis, who were interested in estimating the diffusivity. But we can also translate this to estimate the velocity. And we convolute the solution in the spatial domain with a localized kernel function k delta xk, localized around some spatial point xk with localization parameter delta, and observe some processes continuously in time, x dash dash delta xk, x dash delta xk, and x delta xk, where we just have the scalar product between the solution and some localized function. And the convergence rate depends on the localization parameter delta and the number m of spatial points xk, where we have the local measurements around. So the process x delta xk from the previous display satisfies the equation dx delta xk equals scalar product x of t a star applied to k delta xk with the adjoint operator a star to a dt plus dwt plus some scaled Brownian motion. And we aim to estimate theta at some spatial point x star. So we require some natural assumptions. First of all, the diffusivity A is known. We could also work with unknown and replace it with a sufficiently good estimator. And the velocity theta is beta Hölder continuous for beta greater or equal than 1. And this parameter beta will also appear in our convergence rate later on. Secondly, the supports of k delta xk and k delta xl are disjoint for different xk and xl, meaning that the corresponding Brownian motions wk and wl will be independent. And third, the absolute value, the distance between xk, our local measurement points, and x star is bounded up to a constant by some bandwidth h, dependent on delta. So basically, the assumption 2 and 3 imply that the number of spatial points we can work with is bounded by delta to the power minus 1 h, and this is the maximum we can achieve. Yeah, so as you can see, we can split up our spatial domain into disjoint sets of the supports of k delta xk. And if we decrease delta, then the support decreases as well, but we put more mass around the localization point. And we will work with the local likelihood approach, meaning that we assume that theta is a local constant, but our assumptions are kind of similar to those of a local polynomial estimator of a degree of 1. So we have positive rates which add up to 1, and we force a kind of deterministic design, excuse me, not deterministic, a kind of regular design, and the sum of the squared weights is bounded up to a constant by n to the power minus 1. With this in mind, we can start our estimation procedure. So we replace in the true likelihood the appearing conditional expectation parts with the values ignoring just the conditional part. And this leads to the following maximization problem, which can be directly computed. So basically, we have in the nominator some weighted sum of stochastic integrals minus a compensation term, and in the denominator we have a weighted sum of integrals of squared functions. So the next step is to plug in the x delta xk to get a nicer representation of our estimator. And if we do so, then we can see that the compensation term cancels out, and we can decompose in a bias part in red and a variance part in blue. So we have to control those errors. And basically, we can show that the denominators converge in probability to some constant, while the nominators can be bounded in probability sufficiently fast, which leads to our central theorem. So our estimator is weakly consistent, and under the assumptions A, B, and further restrictions to the kernel K, we obtain the convergence rate in probability h to the power beta plus m to the power minus 1 over 2. And if we minimize this with respect to delta for beta equals to 2, then we end up with convergence rate in dimension 1 of delta to the power 2 over 5, which can be seen on the left-hand side, where we compare with two different kernels satisfying the extra assumptions. And if we fix delta and only decrease h, then we can observe the classical bias variance trade-off on the right-hand side in non-parametric statistics. So what have we learned? Well, first of all, we can obtain the same rate of convergence like in for the local polynomial estimator of a degree of 1, even though we assume that theta is a local constant. This is kind of similar to the Nannerbeyer-Watson estimator in a regular design. And also, our result can be extended to the d-dimensional case with surprisingly improving rate. So there's no curse of dimensionality from a theoretical point of view. And a maximum choice of spatial points m would lead to the convergence rate delta to the power beta d over 2 beta plus d. So for d tending to infinity, this allows for the parametric rate delta squared for beta equals 2. And we can also extend this result to some generalizations, for instance, initial condition, other time horizons or spatial domains, and we could also add some reaction terms as well, and would still get the same result. And what are the next steps we would like to show or do? Well, first of all, it would be very nice to prove that our estimator is optimal, meaning that we have a minimax convergence rate. So this basically requires to prove a lower bound. Secondly, We could work with another observation scheme. So we would have discrete time observations instead of continuous one. And yeah, we can ask questions like, under which conditions can we get the same convergence rate and so on. And third, also extensions to semi-linear SPDEs or a joint non-parametric estimation, where we would also be interested in estimating non-parametric diffusivity, for instance, could be considered. Anyways, thank you very much for your attention, and I'm looking forward for the discussion.